Okay, welcome back everyone to another tutorial video on the theory of computation. In this video, we'll be looking at how to design a PDA which accepts a certain language. So I have already done a few, I had already done a few of these examples during lecture, um, but I think just to do an extra one, I wanted to do this one because it's quite a famous one that people typically show in theory of computation classes. And I think it gives you an extra sort of design trick that might be helpful in the future. Okay, so I want to design a PDA which accepts the language L, which is over the alphabet AB, where all the strings in L have to have exactly the same number of A's and B's, right? And so you'll recall that we've already seen how to design a context-free grammar, right? Which generates this language, right? Recall that context-free grammar was, S gives you SS, then ASB, BSA, and then epsilon, right? So one way you could design the PDA, which would be sort of um, a bit hacky, is you just take this context-free grammar and you use the algorithm to convert it to an NPDA, right? Sure, that's one way of doing it, right? Here there's no specification on whether it should be an NPDA or a DPDA, so that's totally valid. That would work. But that's kind of hacky, right? And so what we're actually going to do is we're going to sort of just design the PDA directly, and I think it's going to be an interesting thing for me to show you. So my recommendation whenever you're asked to design a PDA or whenever you're thinking whether you should design a PDA, try to think of how you could use a stack, right? And then from there, see how you can sort of write down the transition diagram, okay? So I have my stack, right, which I'm going to say starts with the dollar sign at the bottom, because I like the dollar sign. Um, and now I want to see what should my PDA use stack for, right? So imagine I have something like AA. Imagine I have a string like AABB. Then I think an idea probably in the right direction is to kind of use the stack as a counter for the number of A's, right? So, I have two A's, meaning that let's say I just add two A's, right? And then if I see two B's, I decrement my counter of A's, right? So if I see two B's, then I pop them off, right? For every B that I see, if there's an A at the top of the stack, I pop it off. And then at the end, if my stack is empty, and I pushed the same number of A's as I popped the number of B's, then that means I have the same number of A's and B's, right? But this logic really only applies to when I have something like AN, BN, right, for that language. Because now what can happen is now, for instance, I could have, BB and then AA. So now I kind of need a counter for the number of B's, sort of, right? Now I need something like, I see two B's, so I push them on the stack, right? And then for every A I read, if there's a B at the top of the stack, then I pop it off, right? So here I would pop off A, I would pop off B once I read this first A, and then B again. So then I would get an empty stack again. Cool. So, there could be like two branches. Maybe I could use epsilon transitions, one for AN BN and one for BN AN. That might work, right? But then, of course, there is a slight problem. What if I just have a mismatch in order? So would I have BA, BB, A, A, right? Something like this. Okay. Then this gets a bit tricky. I can't just say, well, I have a counter. I just choose that I have a counter for B uh, or just a counter for A. So instead, what it kind of looks like I need to do is I need to create not a counter, but sort of something that accounts for the difference between the number of A's and the number of B's, right? So what do I mean by that? It's actually quite similar to the logic of sort of the graph that I showed you in a previous video. Imagine instead your stack represents sort of the number of A's minus the number of B's, right? And so if you have something like, I don't know, two B's, then this represents sort of like -2, right? So I have two extra B's than the number of A's. If, for instance, if instead I have something like three A's, then this tells me that the difference is something like +3, right? So then what I want, of course, is I want to run through my string. And if at the end of my string, I have a counter, right? I have a difference tracker, not a counter really. I have a counter which is empty, then that means that the number of A's and the number of B's have balanced themselves off, right? So that's kind of what I want to do. So what would be the logic for that, right? Well, let's take this string as a good example, right? So what am I going to do here? So I start with my stack, and then I see a B. So I'm initially in sort of negative, right? I'm at -1. Then I'm reading an A, right? So here I'm reading an A and I see a B, right? So that tells me that I need a transition for that case, right? I'm reading an and I see a B. And what I do in that case is I pop off the B, right? I pop off the B. But um, but this doesn't mean that every time I see an A, I have to pop off a B, right? So we'll see that in a second. Um, so now I have, a B and there's a $sign at the bottom. So let me push a B, right? Then again, I'm at this B. Now there's a B at the bottom, right? But you can imagine, right? There's a B at the bottom, right? So that means I'm just stacking on an extra count in B's, right? So I would add a B here. But you could imagine, right, in an alternative scenario, suppose I had something like B, A, B, right? In that case, right, so this is for this guy. In this case, I would have, I would have push an A, then push the B, then popped the B, and then I would have gotten to an extra A here. So now, if I'm at this B and this is the state of my stack, right? Then what I need to do is I need to pop this A. Right? I need to pop this A because this is like I have +1, right? But now I'm reading the B, so I want to decrement that +1 to go down to 0 in this case. So what I'm trying to say is that what you do based on what you're reading, what you do based on the letter you're reading depends on the content of the stack, right? It's contextual, okay? And so we're going to see why that matters when we actually design the transition diagram. So, if I go back to sort of this example, then in this example, right, I'm reading an A and there's B at the top of my stack. So I pop one B. And then again, if I'm reading this A and there's a B at the bottom, then I pop it again. Okay. But what if I was dealing with this string? So I have B, A, B. Then I have, let's see. Right. So then I have maybe A and then B, right? So if I have A and then B, so I was here, I was reading this B, my pointer was at B, and I was reading A at the top of the stack. That tells me that I need to pop off this A, right? So now I'm back to a counter of sort of NA minus NB equals 0, which is correct, right? Because I'm here and I have two Bs and two As, so that's right. Now I see an A, right? I see an A, and there's nothing on my stack, right? So then I have to push, right? And I have to push an A if I'm reading the letter A, if I'm sort of empty, or if there's more A's. Right? If there's more A's, then I just keep stacking. If there's a $sign, then I also stack. The only way that I don't sort of stack an extra A if I'm reading the letter A is if there's a B, right? Because if there's a B, then that tells me I need to pop. And then the logic is exactly the same for the letter B, right? So here, I'm reading this A and there's a $sign, so then I push an A. And then I'm here and I'm reading B and there's an A at the top of my stack. So this is the only case where instead of pushing a B, right, to sort of add onto the count, I pop off the A. Right? So I pop off the A. And again, I have a stack which is empty, right? And so the condition for sort of transitioning to an accept state would be, you finish reading the string and your stack is empty, right? You could imagine if it was like something like uh, the the number of B's is the number of A's plus one, right? So that tells me I have an extra B. Then the condition would have to be that instead of the dollar sign, I have this B, right? At the top of my stack. Right? I only have a single B, right? So then I would have to check that when I pop off the last B, then I get an empty stack. Okay. Um, but like I said, here we're dealing with NA equals to NB, so we're using sort of this implementation and this acceptance condition for the stack. Okay, so now what does the state transition diagram look like? So let's have our initial state, right? And so actually our initial state is going to do most of the work in this case. So if at my initial state, right, if at my initial state, I read an A, right, and I see the dollar sign, then that just tells me, well, let's of course keep the dollar sign, never push the dollar, never pop the dollar sign, but add an A, right? If instead I'm reading an A and there's a B at the top of my stack, then I have to pop it, right? So just popping the B would be, this gives me epsilon. And the last thing is if I'm at A and I'm reading something like an A at the top of my stack, then I have to push two A's, right? Because I'm popping an A, right? The syntax is if A is at the left, then I'm checking there's an A at the top and I'm popping it. There's no like, just keep it there. So this definitely means I pop it. So I have to now add back that A that I just popped and add an extra one, right? And then the logic is very similar for reading B's, right? So for reading B's, if there's a dollar sign, then I add B at the top. And of course, I keep my dollar sign. If I'm reading an A, then I pop it, right? Because then I'm sort of uh, um, trying to go more negative. Like maybe I have +2 because I have two A's. So now I want to take off an A to just represent +1. And then if I'm reading the letter B and I have a B at the top of my stack, then I just stack an extra B onto it. Okay. Okay. And so then that's the entire logic, right? So this is the entire logic of working with the stack such that, you stack A's up if you're reading A's, and then you sort of, if you start reading more B's, you go down. If you read even more B's, then you go even more down. You add more B's. Then if you read more A's, you go back up. So you can see there's this sort of like a zigzag between going up and down the stack, right? So in the end, right, if I have a a stack which is empty, right? So a stack which is empty would be, I just have the dollar sign at the top. Then I can go to my final state, which is going to be an accept state. And of course here, I don't want to read anything more. I don't want to read anything more. And so if, right, so like you can imagine that at this point, right, the dollar sign, you see that there's a dollar sign, right? So at this point, you have Q naught and you have that your stack is empty, right? So imagine you're in this situation. So your PDA can guess, right, that, oh, that means my string is over, right? That means my string, I finished reading my string, so I go to QF. But then there's more to read, right? So that's a jam and that's a reject, right? So it's the same logic as NFAs. If you undershoot your guess, right? You're too early in your guess, then you just jam and that's a reject, right? But you can see that there is a guessing here. So this is actually an NPDA, not a DPDA, right? Because like if you're at Q naught and you're at some sort of intermediate place where you have an empty stack, then you have choices, right? And choices means you're non-deterministic, so not deterministic. So this is in fact an NPDA, an NPDA. which accepts the language where the number of A's is equal to the number of B's. Okay.